Section 8.7 of your textbook deals with higher roots and rational exponents. The definition of a higher root mirrors the definition of a square root. For example, a number c is a cube root of a if c cubed equals a. Just as square roots can be expressed using radical signs, like the square root of 9 equals 3, cube roots can be expressed using radical signs as well. For example, the cube root of 8 equals 2. In this radical expression, 8 is the radicand, and 3 is called the index of the root. The definition of a square root and a cube root can be extended to nth roots. A number c is an nth root of a if c to the n power equals a. And the expression for the nth root of a looks like this. Now, radical expressions containing higher roots can be simplified using the same processes that are used for expressions containing square roots. So there's a product rule for nth roots. The nth root of a times the nth root of b equals the nth root of the product a times b. And there's a quotient rule for nth roots. The nth root of a divided by the nth root of b equals the nth root of the quantity a over b. Let's apply these rules to simplify some expressions containing higher roots. In problem 1, we have the fourth root of 81. This is simply 3 because 3 to the fourth power is 81. Problem 2, the fifth root of negative 32 would be negative 2 because negative 2 raised to the fifth power is negative 32. In problem 3, we have the cube root of a quotient. So we can rewrite this as the cube root of 27 over the cube root of 64. The cube root of 27 is 3. The cube root of 64 is 4. So the cube root of 27 over 64 is 3/4. In problem 4, we have the cube root of 40. Now 40 is not a perfect cube, so what we can do is use the product rule to express the cube root of 40 as the product of the cube root of 8 times the cube root of 5. The reason we choose to do this is that the cube root of 8 can be simplified to 2. So our simplified expression for the cube root of 40 is 2 times the cube root of 5. How about problem 5? 1,250 is not a perfect fourth power of any number, but it does have a factor that is a perfect fourth power. So we can rewrite the fourth root of 1,250 as the product of the fourth root of 625 times the fourth root of 2. The fourth root of 625 is 5, so our answer is 5 times the fourth root of 2. In problem 6, we have the fifth root of the fraction 13 over 243. In this case, the denominator is a perfect fifth power. So when we simplify using the quotient rule, we can write 3 for the denominator. 13 has no perfect fifth power factors other than 1. So it's already expressed in its simplest form. And our answer is the fifth root of 13 over 3. Now let's consider how higher roots can be expressed as exponents. Consider the following situation with square roots. The square root of a squared is simply a by the definition of a square root. But from the laws of exponents, we also know that a to the 1/2 power squared would equal a. Combining these two equations, we can conclude that the square root of a is equivalent to the expression a to the 1/2 power. Following the same logic with cube roots, we could say that the cube root of a cubed must be a. And also from the laws of exponents, a to the 1/3 cubed must be a, because we multiply those exponents 1/3 times 3. This means that the cube root of a is equivalent to a to the 1/3 power. Extending this idea to nth roots, we have the general conclusion: the nth root of a is equivalent to a to the power of 1 over n. What about expressions containing nth roots and powers? Consider the following equation. The cube root of a squared is a to the 1/3 squared. While raising a power to a power, we multiply the exponents and we can see that we have an answer of a to the 2/3 power. What about the fourth root of the quantity a to the 5th? Well, that would be a to the 5th to the power of 1/4 because of that fourth root. And again, multiplying the exponents, we obtain a to the 5/4 power. Putting these things together to draw a general conclusion, we can see that in the expression a to the m over n power, the m, the numerator of the exponent, is the power of our original expression, and the n, the denominator of our exponent, is the index of our original expression. Let's use these ideas to simplify some expressions involving rational exponents. 16 to the 1/4 power would simply be the fourth root of 16. And the fourth root of 16 is 2. Negative 27 to the 1/3 power would be the cube root of negative 27, which is negative 3. 9 to the power of 3 over 2 would be the square root of 9 cubed, because we have an index of 2 and a power of 3. Well, since the square root of 9 is 3, and 3 cubed is 27, we can say that 9 to the 3/2 power equals 27. What about 32 to the 4/5 power? Well, our index is 5, so we have the 5th root of 32, and our power is 4. So we take the 5th root of 32 and raise it to the 4th power. The 5th root of 32 is 2, so 2 to the 4th power is 16. Therefore, 32 to the 4/5 power is 16. Negative rational exponents function in the same way that negative integer exponents function. So, for example, 64 to the negative 1/3 power would be equivalent to 1 over 64 to the 1/3 power. This is 1 over the cube root of 64, so our answer is 1/4. Finally, look at 81 to the negative 3/4 power. This would be 1 over 81 to the 3/4 power, which would be 1 over the 4th root of 81 cubed. The 4th root of 81 is 3. Cubing the 3, we get 27 for the denominator. So 81 to the negative 3/4 power is 1 over 27.